Charles Kankelborg is an associate professor at physics at Montana State University. His research interests include ultraviolet instrumentation, observation and modeling of the solar transition region and corona, the solar magnetic field. Dr. Kankelborg is the principal investigator of the multi-order solar EUV spectrograph, a rocket-borne instrument for simultaneous imaging and spectroscopy of the solar atmosphere. He is a co-investigator on NASA IRIS mission. He has received the Wiley Award for Meritorious Research in 2010, Presidential Early Career Award in 2008, and Outstanding Graduate Level Instructor Award in 2006. And I'd like to introduce Dr. Kankelborg. Thank you.
Now comes the part where I remember to put it from standby to on and all of that. So I noticed, I couldn't help but notice as I came in, there are these wonderful brochures from NASA that up there that say, well, let's say they say NASA on them. What else do they say? Heliophysics, the science of space weather. So if you want a little broader view of the topic of the sun and why it's interesting and how it relates to the rest of the universe, especially where we live, this is a nifty brochure. I wish I could get that broad in a talk about one satellite mission, but I don't think I'm quite talented enough to open it up that far. So anyway, I'm going to tell you about the IRIS mission, and it's a really simple outline. I'll say a few things about, well, really, first of all, I'll say something about spectroscopy, which kind of, that sounds like starting off on a dull note to some people, maybe. But we'll get through it and talk about what it tells us about the sun as a star, and also about the sun's atmosphere and its magnetic field, and particularly the chromosphere, which it turns out is this really mysterious part of the sun's atmosphere. And then I'll talk about IRIS, which is a NASA Small Explorer satellite mission. Talk about what its goals are and how it's going to achieve those goals, and particularly how we here at MSU are involved in it. Okay, so here we go. Here's the dive into spectroscopy. It's, I've been teaching graduate courses for too long, and that's why I have difficulty remembering that I'm talking to normal people. But let's see if I can do it. So here is the spectrum, the rainbow. The colors all the way from red to blue, and in fact, if you go past blue, past violet, and just sort of keep on going. Up about here somewhere, you get into what's called ultraviolet. And if you go down here past the red, you get into what's called the infrared. IRIS observes up here in the ultraviolet. Now there's some really funny things about this rainbow. This rainbow, or this spectrum, was taken by a nifty widget called an SSEL spectrograph. And what it has done is it's actually taken the rainbow and sliced it into little slices and stacked it up. So actually, it starts from the very bluest, maybe it's up here, and goes down to the very reddest down here. So if you really wanted to spread out the spectrum properly, what you'd do is you'd start with this layer here, and then stick this layer over here next to it, and then you'd keep going around the auditorium like this. And I'll try not to shoot the guy in the projector booth. And so probably by about the time we got all around the auditorium, we have the whole solar spectrum laid out in a whole lot of detail. It turns out that what we're doing when we lay out the rainbow in that much detail is we're looking at the light versus wavelength, really, because color, what we perceive as color with our eyes, corresponds to the wavelength of the light. Now here's the other really strange thing. There are a few colors missing. There's the biggest hole right there, but there are lots of little ones too, and quite a few medium-sized little gaps in this spectrum, colors that the sun seems to have forgotten about and left out. And each one of those is called a spectral absorption line. It corresponds to some particular atom in the sun's composition that absorbs the light before it reaches our eyes. And so these little gaps tell us things like what the sun is made of, and it even tells us things like its temperature and how that temperature varies as you go deeper and deeper into the sun. And it tells us things even about how fast things are moving. You know, the police have this thing called a radar gun. And when they shoot you with it, you don't die, it just takes money out of your wallet. And the way that thing works is they bounce radar waves off of you, and if you're moving toward them, it makes those waves get compressed or shortened up a bit. And if you're moving away from them, it makes the waves sort of stretch out on reflection. And that shortening or lengthening of the waves, if you sort of transpose that, if you're a musician, you know what transposing is, into the visible spectrum, that would correspond to a little color shift. So you know, this little line right here might move a little to the right or a little to the left. And what that signals is that something is moving toward you or away from you. This would be really handy, wouldn't it? I mean, if you were, say, just standing outside and you saw something falling out of the sky, and it wasn't moving to the left or to the right, you'd start to think maybe it was headed straight for you, right? Well, it might be handy in everyday life to be able to tell whether things are headed toward you or away from you, and that's what spectroscopy will do for you. So little measurements like this of the wavelength of light are really important. They've revealed to us all kinds of things about the sun. I remember my advisor gave a lecture once to the materials science department at Stanford because there was some nifty materials science in the instrument that we had built to observe the sun. And one of the materials scientists, or maybe it was more like a materials science graduate student, his question was, well, why would you study the sun anyway? Isn't it just a big ball of gas? And well, yeah, that's true. So what about this big ball of gas? It has a luminosity, or if you like, a wattage. 4 with 26 zeros after it, watts. That's the wattage of the solar light bulb. And it has a mass of 2 with 30 zeros after it, kilograms, and a radius of 700 megameters. A megameter is a million meters, or if you like, 1,000 kilometers. So it's kind of big, and kind of heavy, and pretty bright. And here's the recipe if you want to make one yourself. You need about 74% hydrogen and 25% helium. And the last little bit is what astronomers call metals. And if you are a materials scientist or an engineer or something like that, you'll be surprised to know that metals include things like nitrogen and carbon and silicon and stuff like that. Pretty much anything else on the periodic table besides hydrogen and helium, we astronomers call metals. Perhaps because of lack of imagination, I'm not sure. So you combine all of this stuff, you mix it up, and the neat thing is that you don't actually have to heat it up. It will do that itself just by the very act of falling together and collapsing on itself. It will release enough energy to light itself up. And so there's no need to bake. The recipe is self-completing. So there you go. What more could there be to learn about the sun? If you take those ingredients and just apply ordinary physics to it, and by ordinary I mean the sort of physics that we had by, say, 1930 or so, then you find out that the sun must have the following structure. It has a core in which the pressure and the temperature are very high. And that accounts for maybe the first quarter of the sun's radius where nuclear fusion is going on because of that high temperature and pressure. That is the sun's power source. And then a little further out, it turns out that the heat from this power source is flowing outward primarily by radiation. That is, light just sort of bounces from atom to atom, slowly working its way out. A very inefficient process, so that if in fact you turned off the engine in the middle, it would take quite a while for the light to stop coming out of this thing, unlike a certain Star Trek movie that I otherwise really like. So there you go, and in the middle, by the way, it's you know, up to maybe 14 million Kelvin right at the center, and it gets cooler and cooler as you go to the outside. If you don't like the word Kelvin, if you don't like Kelvin degrees, then think of Celsius degrees because they're practically the same, especially when you're this hot. Okay, and then we have this thing called the convection zone. This is a place where the gradient in temperature is very steep, going from millions of degrees in here to just thousands of degrees on the outside. And because that change in temperature is so steep, it gets the gas really churning around by convection. And so out there, the transfer of heat from the inside to the outside is actually pretty efficient. And then by the time you get to the outside, this thing that we call the photosphere, that's the layer that you see with your sunglasses. And overall, this thing is a wonderful demonstration of just all kinds of different physics. You've got nuclear physics in the middle, you've got radiation, emission and absorption, and quantum mechanical processes going on here. And then you've got the hydrodynamics or fluid dynamics of convection going on in the convection zone, and then more radiative transfer as that light gets emitted from the photosphere and streams out into space. So there you go, that's kind of the standard model of the sun. And this part actually is really well understood. So you might think, I've covered it from the middle to the outer edge, what more could there possibly be to learn? Well, let's digress for just a moment and talk about where this thing fits in the context of other stars. Other stars also have a mass, and they have a recipe, right? A sort of a composition of elements. They have sizes, colors, temperatures. They have a brightness in watts, an age, and a lifetime. They have an evolution or a development throughout their lifetime. And here's a nice example of this globular cluster called M72, discovered by Charles Messier and photographed here by the Hubble Space Telescope. You see a lot of variety. You see brighter stars, dimmer stars, stars that are kind of red, stars that are kind of blue. It's quite a heterogeneous family. And astronomers like to use this fancy diagram, which indexes the stars by color, getting bluer as you go to the left, red is toward the right. And that corresponds actually to the overall temperature of the star, and then also by their luminosity or their wattage as you go up this way. It turns out that if you arrange the stars on a diagram like this, they can't fall just anywhere. They tend to fall in preferential spots, the most prominent one being this thing called the main sequence. And there's our sun right in the middle, in some ways the most average of stars. And it turns out that, in fact, this whole diagram now can really be reproduced by stellar models. That is to say, there are people who can run a model of this thing just using ordinary physics on their computer and predict the characteristics of stars anywhere on this diagram. And not only that, they can show how stars form, how they fall onto this main sequence, and how later they peel off and become other types of stars at other points in their lives. And also how they may eventually fall down here as white dwarfs once they've collapsed. So again, not only the sun, but other stars seem apparently well understood. And so that's why you cannot leave today, because if you did, you would tell the world that we already understand the sun and we wouldn't be able to launch our cool satellite. And so I'm sorry about that. I wasn't supposed to let the secret go. All right, so here it is, the outside edge of the sun, right? And we understand all the stuff inside of that photosphere, or so I've said. That may be a slight exaggeration. But here's the first hint that something might be wrong with our understanding, this little thing called a sunspot. Then, if we look with an H-alpha filter, how many of you have looked at the sun through an H-alpha filter and know that you have? Okay, so there's a good couple dozen people here who have. And this is a view of what we call the chromosphere. This is a layer that sits on top of the photosphere, and it has a lot more features on it. These funny little filaments and these bright areas called plage. It's, the sunspots also show up very well here. And the chromosphere, it turns out, has a temperature around 10 to the 4 kelvins. This does not come out of the standard solar model. We just measure it, and we wonder. Then, there's this thing called the transition region, which is on top of that, and it's another factor of 10 hotter. and is remarkable in part because it is merely a transition as you move up higher and hotter to stuff like this. This is the corona of the sun, which extends out into space and has a temperature of from 1 million degrees up to maybe 10 million degrees, and in some cases hotter. So there is something very strange going on here. And I apologize if you heard this little joke before, but what I like to say is, I opened my fridge and there was a glass of ice water sitting there, which seemed perfectly normal, and the only abnormal thing was the flames leaping off the top of the glass of water. That's what the sun is like. Okay, the refrigerator is space. We all know that space is cold. The glass of water is the hot thing known as the sun. That's 5,800 degrees, but compared to it, the flames leaping off of it, the corona, are awfully, awfully hot. And that's something of a mystery. Iris, by the way, is interested in this layer, the chromosphere and the transition region, the sort of thin layers that are in between the photosphere and the corona. You might think we're missing the interesting bit, but I'll argue that we're really not. In any case, there are big mysteries about this. The heating in the first place, how does this outer atmosphere get so hot? And also there are these really amazing events called coronal mass ejections and flares that are very impulsive releases of energy that send stuff spewing out into the solar system. There's also the acceleration of the solar wind, which is a more or less steady breeze of material blowing off the sun. And there are also strong magnetic fields on the sun, as I'll discuss in a moment. Here's why those little transition areas, and particularly the chromosphere, are particularly interesting. If you want to know what heats the corona, that takes about 300 watts for every square meter of surface on the sun to heat the corona above it. It turns out, though, that the corona is not very dense. And so if you really want to understand the heating of the atmosphere, what you really want to understand is the heating of the denser part, the chromosphere, which, though not as hot, has enough material to be heated that you need more like 5 kilowatts per square centimeter to do the job. Now, these numbers are still small compared to the light that streams off in just ordinary visible light every day. The thing is that there's no real plausible way for that light to heat the chromosphere or the corona to the degree that they're heated. So that's why there's a mystery, and that's why the chromosphere is an even bigger mystery than the corona, even though it doesn't seem quite as spectacular. It may, in fact, be that once we solve the problem of the heating of the chromosphere, the corona will end up being some sort of small footnote in the story. Or at least that's what we say when we write the proposal for the satellite. It's fun, I think, to go back to the past a little bit. This is a book that was published in 1896. I actually have the 1897 edition of this textbook by C.A. Young about the sun. And at this early date, people had pictures of the chromosphere. Now, photography was a pretty new thing, so they were still doing a lot of sketching, just like Galileo did. But they had this nifty device that was a combination of sort of a spectroscope and a telescope and a thing to block out most of the sun except for the very edge. And this allowed them to sort of catch the chromosphere right on the edge of the sun there. Normally you can see it during a solar eclipse. Anybody seen a solar eclipse? Oh, wow, a bunch of people have. Did you see that red stuff sticking out from around the edge of the sun? That's the chromosphere. You probably knew that already. But anyway, there it is. There's the chromosphere. And they see all these interesting, strange features, these prominences that stick up, and some of them look like trees or like smokestacks or barbed wire or just all kinds of strange stuff, shark fins, whatever, sticking up off of the sun. Here are a few more sketches. Whoops. A few more sketches from the same book. And here's actually an early photograph. The photographs don't look nearly as good as the sketches, unfortunately, but this gives you an idea of what they were doing. This is not a solar eclipse. It's sort of an artificial eclipse generated by a disk sitting in the first focal plane of the instrument, where the light first forms a solar image, and you let the other fainter stuff get by around the edge so that it's easier to see without the bright disk in the way. Here's a solar prominence photographed. And all this stuff was going on. A number of people were doing it. George Ellery Hale, there's Hale's name if you can see it, was one of the big people in this field, and it says here, in the great spectroheliograph now building under Mr. Hale's direction to be used with the gigantic 40-inch equatorial of the Rockies Observatory, the slits will be fixed in the spectroscope, but the whole spectroscope will be so arranged in the framework which attaches it to the equatorial that it can be moved bodily across the 7-inch image of the sun while the plate holder remains fixed. Students of solar physics await with great interest the outcome of the new methods and apparatus. I loved that. Now, unfortunately, for this fellow who had written this textbook, only about 11 years later, George Ellery Hale, who he was just talking up there, learned something that pretty much made his whole textbook obsolete. And this is what it was. Here we have a picture of a sunspot. This is not Hale's original picture, but it's one that's almost as indistinct. And there's a spectrograph slit right over the top of it here. So that is where the spectrograph is pointing, and this is the spectrum that comes off of it. Let's see if we can understand it. There's kind of some dark stuff here with little light bits sticking through. Well, look, we've got dark, light, okay? So what's happening is the light from this slit is getting spread out horizontally, spread out to the sides. And so wavelength runs from left to right. And the direction along the slit is up and down here, just as it is in the photograph to the left. So what we're seeing are patterns of bright and dark on the surface of the sun, but spread out by wavelength. Here are a couple of those absorption lines in the solar spectrum. And look at this one here. It looks like somebody sliced it up and spread it out. That's called Zeeman splitting, and it means that there's a really strong magnetic field here in this sunspot. And that was the big discovery, that sunspots basically are places where there's a really strong magnetic field, strong enough even to slow down the sun's convection so that the surface is allowed to cool down a bit, and hence it's not so bright. And that, it turns out, is part of the big story behind sunspots. Here's a sunspot, much more modern picture taken in 2002 from a Swedish telescope on the island of La Palma. If you ever get a chance to go to the Canary Islands, you really should. It's a beautiful place. And here we see the sort of roiling convection in most of the solar atmosphere is like this. And then as you get closer to the sunspot, that convection gets modified. I'm sorry the movie is so jerky. I'll blame it on PowerPoint. Couldn't be my movie. So anyway, I don't know, it's pretty. Here's another picture. This may be from the same telescope, showing a thing that's like a sunspot but smaller. This is called a pore. This is on the same scale. Here's the radius of the Earth, about this big, 6 megameters, just to give you scale. And all these little granules, so-called, are convection cells where warm stuff is coming up from the interior, spreading out, and then sinking down after it's cooled. Right on top of that, then, now that we've talked about that little bit, here's that solar chromosphere that I was promising to talk about. This is a picture actually taken by a very competent amateur. Anybody here ever take one this good? I haven't. Not of the chromosphere. I've taken some nice pictures of the corona, but this is really spectacular. It's one of the best I've seen from anywhere, professional or amateur. And what you see are these filaments of matter suspended by magnetic field over the surface of the sun, sort of medium temperature gas that's just kind of hanging there in a magnetic canopy. And these little barbs and spicules of material that has a really sort of a hairy filamentary appearance because of the magnetic field. Doesn't it sort of remind you of the iron filings on a card with a magnet underneath? And here's the thing about the chromosphere. It's guaranteed to outlast my physics career because it has so much physics going on all at once that there's no way to put it all together and make sense of it. It's fantastically complicated. In every layer of the sun, there's something that you can throw out, something that you can ignore. Up in the corona, for example, the gas is so thin it doesn't absorb any light, it just lets the light stream right through it. That makes things a little easier. Also in the corona, the magnetic field is so much stronger than the gas pressure that we don't worry about gas pressure. We just say, what's the structure of the magnetic field? The gas has to follow that. So the corona is easy compared to the chromosphere, where none of those assumptions hold. Here's a picture of the chromosphere, a movie actually, from the Solar Optical Telescope aboard the Japanese Hinode satellite. SOT was built by our Lockheed collaborators here in the US and then put on this Japanese spacecraft. This is a movie taken with a filter that takes only one of the calcium absorption lines. You can see these little spicules that pop up and down, little filamentary things all over the surface. And they can move 5 million meters in a few minutes. They're really amazing. So that's another thing about the chromosphere. There are parts of the corona that just sit there for a while. The chromosphere never stops moving. It's never steady. And so the element of time is extremely important. Nevertheless, there are people who manage with very sophisticated computer models to model aspects of the chromosphere. This is a computer model from the University of Oslo of chromospheric waves, that is waves propagating upward through the solar atmosphere. The neat thing about this modeling is that it's just getting to the point where we can start comparing this stuff to what people actually measure on the sun. So here's a spectrograph observation of a particular absorption line where there are these waves traveling along, and it distorts the shape of the spectral line. Remember how I was saying you move the spectral line a little in one direction, it means stuff is moving towards you. Move it a little the other direction, it means that stuff is moving away from you. So here we go, a wave is stuff that's moving sometimes toward you and sometimes away from you. Well, so this is actually the simulation and this is reality. They don't match up perfectly, but it's starting to get to the point where the models are actually useful. So we got all these mysteries we'd like to answer, like, you know, what is the way that the chromosphere modifies the flow of energy and matter from the interior out into space? And what causes these solar flare things anyway? Is that something in the chromosphere, or is it actually triggered further out? What accelerates the solar wind? Do we have waves propagating all the way out through the chromosphere and into the outer atmosphere and ultimately towards Earth? There are all these questions that we would like to answer. And IRIS is a mission to answer a great many of them. Not all of these questions can be answered entirely by looking at the chromosphere, but all of them have some piece that we can't get past, where we have to learn about the chromosphere before we can put the rest of the puzzle together. You know, it's like all the edge pieces were hidden under a cushion on the sofa, and all this time we've been trying to put this thing together, and the chromosphere is the edge pieces. So, IRIS, what is it? The interface region imaging spectrograph. There, that settles it, doesn't it? Interface region just means that thin layer called the chromosphere. The institutions involved are Lockheed Martin, that's a different part of Lockheed Martin, and Acton Research Corporation that does the coatings on our mirrors, Smithsonian Astrophysical Observatory, which is another word for Harvard, University of Oslo, they're the modeling people. Without their help, we won't understand what our observations mean. Montana State University, I'll talk more about our role in a moment, and Stanford University. So, if you're an up-and-coming graduate student around the time that this thing launches, your choices, if you want to get involved, are to go to Stanford, Harvard, Oslo, or Montana. So, the principal investigator of the mission is Alan Teitel at the Lockheed Martin Solar and Astrophysics Laboratory in Palo Alto, California. We plan to launch the thing in December of 2012 into a sun-synchronous orbit. That means it goes around the Earth above the division between night and day. And the orbit is tweaked in this interesting way so that it keeps going around to face the sun this way. So you're always just looking out over the horizon at the sun, which is really kind of nifty. It's a 2-year mission, nominally. Hopefully we build the spacecraft so that it'll last a little longer than that and can convince NASA to extend our funding when it's giving great results. It'll take images and also spectra in the ultraviolet with a really good spatial resolution. What's an arc second? It's a 60th of a degree. What's a degree? It's twice as wide as the full moon, or if you like, the sun on the sky. So take that sun, divide it into 30 pieces, and oh no, that gives you arc minutes. Divide that into 60 pieces, and then you get arc seconds, and we're at 1/3 of an arc second. That's the size of the detail that we can see. Very, very fine detail. And we plan to take 1-second exposures all day, every day, until they turn off the spacecraft or revoke our funding. So, and that's what the satellite is supposed to look like. Here's a bigger view of it. There's a telescope on the front, which feeds directly into this box, which is our spectrograph and our imager. There's a little guide scope on it. Most of you who have telescopes have guide scopes. How many people here have a telescope bigger than 8 inches? Okay, how many people have looked through a telescope bigger than 8 inches? All right, this is an 8-inch telescope, all right? It's $105 million worth of 8-inch telescope. It costs a lot of money to put it in space, but part of the reason it's so expensive is the whole ultraviolet thing, and another part is because of this very fancy spectrograph put back here. So I guess part of the moral of the story is that you don't have to have a 1 meter or a 10 meter or a Boeing 737 sized telescope to make new science. I think that's kind of cool. Here's kind of a cutaway view. Those of you who have a Cassegrain telescope or have looked at one, maybe some of you amateur telescope makers will recognize that donut as the primary mirror of a Cassegrain telescope. There's the secondary mirror, so the light comes in here, bounces, bounces, and goes back into our spectrograph, where everything gets really complicated. There's our guide telescope, which is just a little refractor, probably about I think it's maybe a 1.5 or 2-inch refractor, something like that, with a fancy detector on it that keeps us pointed at the sun. Well, no, okay, the detector can't keep us pointed at the sun, that's a lie. The detector tells us when we're off, and then there are other systems on the spacecraft that fix it. Here's the optical concept. Now here's where I'm tempted to teach a physics lecture, but I'll try to keep it short. Do we have any amateur telescope makers in the audience? Oh, not as popular as it used to be, I guess. Gosh, when I was a graduate student, there were lots of amateur telescope makers in the world. Well, okay, so here's that Cassegrain telescope I was telling you about, the thing that gathers all the light and then focuses it back into our spectrograph. This is the slit of the spectrograph. That really, what it does is it picks off a little slice of the sun to spread out in wavelength. So this bit here is the spectrograph, very fancy thing. This grading is why I got to go to France in December and take my wife and daughter. Don't worry, NASA didn't pay for my wife and daughter. I paid for them, but NASA paid for me to go. And this part over here is a clever little bit that gives us a picture of the sun from the light that didn't go through the slit. The slit is shiny, so we can pick off the light that didn't go through it and form an image of the sun over here. And what that does is it gives us a big picture of the sun with a dark line on it. Because there's nothing more frustrating than to have a spectrograph and see this lovely spectrum and have no idea whatsoever what part of the sun you're looking at. So that's why we have this thing. And also because it'll make lots of pretty images, and it'll make it a lot easier to understand what we're looking at with this one little slice. Okay. Here is an eye chart. Why do I have this slide? Well, I suppose to reinforce the idea that here you go, here's an image of the sun and here's the dark line. Okay, it should be a dark line where the slit of the spectrograph is. And if we want, we can scan the slit from left to right. We can take an exposure, move it over, take an exposure, and so on, and build up the spectrum of a whole region on the sun. Or we might even just sort of move the thing a little faster, take bigger steps, and cover a whole interesting feature on the sun, take spectra on all these slices. This chart is just a list of spectral lines that we can observe and how bright they are. This is the how bright part. And the really bright spectral lines, the ones that are very easy to see, give us 10,000 degrees, 20,000 degrees, 70,000 degrees, and then we have corresponding filters down here. This is for the imager part. so that we can sort of get good context for any of these choices up here. So it's a nifty thing. Now, why in the world is MSU involved? What are we doing? Well, our job is to help with this spectrograph and the slit jaw imager that go behind the telescope. The Harvard guys build the telescope, and we contribute aspects of the spectrograph. We built a nifty breadboard prototype in my lab. We are specifying, procuring, and testing all of the custom flight optics that go into that spectrograph box, or at least nearly all of them. And it's also our job to help the Lockheed team with the design and with putting the thing together at their facility in California, testing it, calibrating it, and then when we launch it, we all get to participate in the science and data analysis together. Also, Montana Space Grant Consortium is doing the education and public outreach, or a big piece of it, for the mission. NASA, all NASA missions have education and public outreach, which is a great thing because, I mean, if your tax dollars are paying for it, why shouldn't we at least have public lectures or something and tell you what it is? Oops, how did I do that? There we go. This is the list of people at MSU who are deeply involved in the project. Not so many, less than a dozen of us. Here's that breadboard I was telling you about, the first prototype of the instrument. So it was very fun to do this. I spent just a week ordering all the parts, and a postdoc named Nathan Poost, who's really talented, put it all together and got it working. It's all built from just commercial catalog items. And in fact, it's actually fairly close to the Iris optical design, just the mounts and such are not the sort of thing that you would fly in space. You fly this thing in space, the mirrors would go flying out as soon as you launch the thing. But it was our optical proof of concept. And it was very inexpensive and a great learning tool for us as we were in the design phase. One of the nifty challenges for this thing, and since I know now that we have no amateur telescope makers at all, I wonder if I can explain this. This thing is supposed to perform about as well as an instrument of its aperture size can, which means that the limiting factor in observing details on the sun will be, hopefully, the wavelength of the light itself, in some sense. And so that's what we call the diffraction limit. What it all comes down to, what it all boils down to, is that our mirrors need to be polished extremely well, and they need to have exactly the prescribed shape. The prescription can't be off, because if it is off, and in fact, if the average error is more than a couple of nanometers, which is the diameter of this strand of DNA, you were wondering why the DNA was there, then it won't work. Part of that is just because any instrument of this resolution would have to be very good. Part of it is that this particular instrument has 6 reflections in it. And so we have what you might call an error budget. And no one mirror can have all of the error in it. The error has to be shared among all 6 reflections. And so as a result, we have a tight budget for this error accumulating as the light reflects from mirror to mirror through our instrument. So this is challenging. It means, for one thing, that we need to measure the surfaces of this mirror to within something like 1,000th of a wavelength of visible light. And it also means that the mounts that we use in our instrument have to be very good. Telescope mirror mounts, for the most part, tend to bend mirrors. You know, it would be really ideal if you could make a telescope and just kind of set the mirror there and have it float. Anti-gravity technology would be the right thing for building telescopes, and then mirrors would not sag and bend, and they wouldn't get sort of crimped by things grabbing onto them. However, these mounts also have to survive being more or less drop-kicked when the satellite is launched into space. So those are contrasting requirements that make it difficult. Here's the lab that we set up at MSU to do the measurements on these mirrors, again measuring them to much smaller than the width of a strand of DNA to assure that we can meet the instrument error budget in the end. I have no idea who these people are. One of them might be Christy Dunn, who's our excellent optical engineer. Dr. Dunn will be giving a talk 2 months from now, is that right? I think that, yeah. So come and watch that, and she'll tell you how she figured out how to grind and polish the mirrors for the extremely large telescope. The very same measurement technology that's being used for that giant European telescope, this nifty type of interferometer, is what we have for measuring our teeny tiny mirrors. It turns out that it's exactly the right tool. And lest you doubt, here's a measure of the surface topography of one of our mirrors. The root mean square deviation of this whole mirror, which is about a 4-inch mirror from its nominal shape, is 2.5 nanometers. And fortunately, the 2 nanometer spec really only holds over little sub areas of it, or this optic would be out of spec, but it actually turns out it's in spec. It's good enough. All right, so let's see. We're now at 7:46, and I'm nearly done with all of my slides. I must have moved kind of fast. Did it feel fast? Yeah. Okay, well, good. I'm always worried I'll go too slow and put everyone to sleep. You don't look like you're asleep. I only see like 3 or 4 people sleeping, so that's pretty good. And so now I got to talk about a nifty fun thing that I really only had time to prepare 1 slide about it, but it's very fun. The IRIS outreach project that I referred to earlier that Space Grant is running from MSU is a national student spectrograph competition. So the idea behind it is this. We will get college student teams building their own spectrographs. Now, we're not going to like send them a plan or a kit or something like that and say, here, build this. And we're not even going to say, build an instrument that will do such and such. We're going to say, suppose you wanted to point a spectrograph at the sun and learn something. What would your science goals be? Come up with your science goals and figure out how to design an instrument that would meet your science goals. Go ahead and build the thing, and if you do a good enough job, we'll let you come to Montana for the final runoff. There'll be some number of teams that actually travel here and compete, 28, I believe, and then if we have a clear day, they'll point their spectrographs at the sun. If we don't have a clear day, then maybe a couple of days later we will. But in the meantime, we'll have some other interesting light sources with nifty spectral features for them to point their spectrographs at and test them. We have right now a pilot program going with 2 teams, one at Salish Kootenai College, one at Montana State University. And I'm given to understand they actually have built prototype spectrographs at this point, and or at least have kind of a design. And they should be ready this spring to come to MSU. We'll test out our apparatus for holding the sun steady in the sky. It was really hard to build a big arm reaching out there 93 million miles to hold the thing still. And they'll point their spectrographs at the thing and take data. Actually, as you might imagine, it's a tracking mirror that holds the sun steady. So that's the deal with the spectrograph competition. I'm very excited about this. I get to be one of the judges. There's another fellow named Christopher Palmer, who is a pioneering figure in spectroscopy, who will be here from Newport Corporation. He runs an operation within Newport that used to be called, well, I guess it still is called, Rutherford Grading Lab. The Rutherford Grading Lab builds these nifty things called diffraction gratings, which I am a big fan of. They're the things that make spectroscopy possible. What they are is a little square glass that's funny. Sounded kind of strange there, didn't it? Oh. How about if I turn it off and talk loud? All right. So what's a diffraction grating? It's a little square glass that's very shiny and very precisely figured, just like one of the precision flat mirrors that we would put in the spectrograph, except that it has been very intentionally scratched up. And the little scratches, there are 3,600 of them per millimeter, very evenly spaced, and it's a poltergeist. Ha! Very evenly spaced, and those are the things that we actually use to measure the wavelength of the light in the spectrograph. They spread the light out by wavelength across a detector so that we can see what we've got. Anyway, Palmer is an expert in building these things, and RGL has been around for years. It's floated from company to company. It's one of these operations that's been bought by this company and then sold, and then that company went bankrupt, and then they got bought off by this company, and they've been around for probably 50 years or more. But it'll be a real pleasure to have him here. And here's the other reason I like diffraction gratings. It was the diffraction grating from France that let me go to Paris. I knew there was another reason I liked diffraction gratings. I also like French wine. All right, well, that's about it. I'll throw up my conclusion slide, which just says that the solar chromosphere is this beautiful, complicated, interesting thing that we get to look at. IRIS, the satellite mission, is poised to solve some of the big mysteries, hopefully not all of them, because I want to keep working in this field. And it's also MSU's first major role, hardware role, in building a scientific satellite. So that's also quite exciting. We have a student opportunity to build ground-based spectrographs via this competition. The satellite itself launches in 2012, we hope. And here are a couple of websites that you might want to check out. There's the IRIS website, iris.lmsal.com. And then there's also the website, the MSU website about IRIS, which includes this student spectrograph competition, so spacegrant.montana.edu/iris.html. So have a look at those if you want. There's lots of neat stuff, much more than I could talk about. And as a parting shot, this last picture here that you can faintly see, this is a DC-10, somewhat modified by a company called Orbital. And this little thing flying underneath it is a widget that was dropped from the underside of the airplane. This is a rocket for launching a satellite. The Orbital scientists pioneered this technology. It's the greatest use of cruise missiles ever. And it starts flying out horizontal like that at like 30,000 feet, and then it just kind of takes off and puts the satellite into orbit. So that is the type of launcher that we'll be using for this mission, God willing. Thanks for your time and attention.